Good morning, everyone. My name is Vikram Sridhar, and I'm a final year PhD student. So today I'll be talking about my project, which is on understanding the unsteady fluid dynamic behavior of cavities at supersonic speed. When I say supersonic, it means traveling faster than the speed of sound, so maybe around 1500 kilometers per hour. So cavities are basically rectangular cutouts found on the aircraft structure in the form of Bombay doors. Consider this F-22 Raptor, which can go at supersonic speeds. Now, in order to launch a missile, the aircraft has to slow down to subsonic speed, which is less than the speed of sound, and then launch the missile. But at supersonic speeds, what happens is, when the Bombay doors open, there is a cavity is formed, which causes unsteady fluid oscillation. Now, these oscillations produce shock waves below the cavity and can lead to severe vibrations and fatigue. Now, this can cause failure of the release mechanism, and hence the aircraft will be unable to launch the missile. Now, apart from the disadvantage of cavities, cavities are nowadays being used in scramjet combustors, gas turbine engine combustors as flame holding device. Cavities are known to give better fuel mixing and also avoid flame burnout. Cavities are mainly classified based on their length to depth ratio. They are called open cavities if their L by D is less than 10, closed if it's greater than 10. So in the case of open cavity, the boundary layer, which is essentially a slow-moving fluid, separates at the leading edge of the cavity and forms a shear layer. Now this shear layer impinges on the trailing edge and creates a pressure wave which travels upstream inside the cavity and disturbs the shear layer at the front. Now this causes a feedback loop and produces discrete resonant frequencies. Now in the case of closed cavities, the shear layer hits the cavity floor and reflects and reattaches at the trailing edge. Now, as you can see, there is no feedback mechanism present, and hence the oscillations are broadband. Now, as I said before, the reason why I'm trying to understand this unsteady fluid dynamic behavior is you can devise control mechanisms such as active or passive to suppress the undesired resonance present in open cavities. Now, previous research was done with limited parameter variation, reliance on single diagnostic tools, etc. And the control techniques what previous researchers have applied have had mixed success. They were not able to completely suppress the oscillation. I also tried to uncover any other mechanism causing the cavity resonance if present. Now, I try to achieve my objectives using numerical simulations with two different computational fluid dynamic codes. And one is an in-house code Elmer 3, and the other is a commercial CFD package fluid. I also do experiments in wind tunnels, which involves high-speed flow visualization techniques such as Schlieren. Schlieren is basically an optical technique where you can see the changes in density of air invisible to the naked eye. Now, if you look at this image, it shows a Schlieren taken for a candle. So you can see the hot air rising above, which is invisible to the naked eye. Now, consider the shorter cavity, which has a length to depth ratio of 3. And you can see that there are waves bouncing back and forth, and the shock waves present below the cavity. Now, this cavity can cause severe vibrations and fatigue. Now, when I move to the longer cavity, which has a length to depth ratio of 8, you can see all the unsteadiness seen for the shorter cavity are smeared out. You do see some shock waves, but they are really weak. Now, what I did is I looked at 4 different cavities, 3, 5, 6, and 8. And when you plot the overall sound pressure level, which is an indication of the unsteadiness of the cavity, you can see that after L by D of 5, the experiments and the in-house code predict that there is a sudden drop in the unsteadiness level, whereas the commercial package Fluent shows that the unsteadiness level drops after L by D of 6. Now this doesn't mean that we can use longer cavities for launching missiles at supersonic speed, because the drag caused due to the longer cavities is quite high. It's more than 100% compared to the shorter ones. Now this graph also shows the disadvantage of reliance on single diagnostic tool. The next, I look at axisymmetric cavities, which are mainly found on missiles and rockets in the form of separation stages. Now, the flow phenomena is similar to planar cavities, which I showed previously. The L by D of 3, which is the shorter cavity, is more unsteady than the longer one. Now, this is an optical technique called streak clearance, which was done previously by using a camera and imaging a narrow region of the flow and recorded on a rolling drum. Now, what the final image gives you is something called a time versus distance diagram, or in simple terms, XT diagram. Now, from that, you can always calculate the velocity of the pressure waves moving, or even the frequencies. Now, in my work, what I did is, since those cameras are very expensive, I took the normal high-speed Schlieren images, extracted a narrow region in the cavity, and placed them on top of each other with a simple program. Now, from this picture, you can the streak clearance for L by D of 3. You can see there are waves bouncing back and forth. Now, you know your time and you know your distance, and if you calculate the velocity, and from that you can get the frequency, and this frequency will always match with the frequency spectrum obtained from the pressure transducers. Now, the advantage of this technique is that you can devise control mechanisms targeting particular frequencies, because you know the flow phenomena which is causing that particular frequency. Now, finally, to conclude, lower L by D cavities are detrimental in terms of vibrations and noise levels. Longer L by D cavities are detrimental in terms of drag. For scramjet engine or gas turbine combustors, lower L by D cavities give better mixing, but are not good as a steady flame holding device. Whereas longer cavities, although they are a steady flame holder, but the mixing efficiency isn't that great. Now, and we have shown the main reason for the unsteadiness in cavities through streak clearance, which I discussed earlier. And we have found very good agreement between optical pressure measurements and numerical simulation. Now, with all this data, we can devise control mechanisms, and hence we'll be able to launch missiles at supersonic speeds. That's it. Thank you.
Thanks for that. The question I have is, so you've shown these basically as L&D experiments or results. Where do they, and you showed the F-22 Raptor before, where you spoke about weapons bays being an issue. Weapons bays are generally fairly shallow compared to the length of the weapon bay. Is there anywhere on the aircraft where it is the other way, that the depths of the cavities are higher than the length?
I mean, generally the weapons bay have an L by D ratio of 5 or 6. Yeah, but you can always find them on structures of the aircraft, like on the wings or something, where you have the flaps. So in between that you have like a depth, a L by D of like 3 or maybe 2, something like that.
Are there issues there?
Yeah, I mean, you do have some issues, but we are mainly focused on bomb bay doors because.
Thank you. Thank you.